This is the third lesson in sequences and series. Last lesson we looked at arithmetic sequences or progressions, and this lesson we're going to learn about geometric sequences or geometric progressions. And by the end of this lesson you'll know about the terminology used for geometric sequences and be able to perform calculations associated with this type of sequence. So a geometric sequence has a common ratio between its successive terms. Last lesson with arithmetic sequences, it had a common difference. This time it's a common ratio. And so if we divide one term by the term before, we get a common ratio, and we denote that by the letter R. We still use A as the first term. So to get the nth term, we simply multiply the term before it by R, and that can be seen in this formula here. And there's our first term A still being used. And so, for example, if you have a look at the numbers here, 6, 12, 24, 48, hopefully you can see the pattern in those numbers. Our first term, which we use as A, would be 6, and our common ratio is 12 divided by 6, which is 2. And you can see that 24 divided by 12, 48 divided by 24 all give you that common ratio of 2. And so if we have a look at the way that this sequence is set up here, the first term is A. The second term, we multiply it by R, so we get AR. To get the third term, we multiply it again by that common ratio, so we get AR squared. Multiply again by R, and we get AR cubed for the fourth term, and so on. And so you can see that generally the nth term of that particular sequence is given by this formula. And again, this is one that I would highly recommend that you commit to memory fairly quickly. Write it down each time so that you get used to it. So let's jump into our examples. The first one says, find the 15th term of the sequence 3, 6, 12, ... So our formula is Tn equals AR to the n minus 1. And so our first term is 3. Our common ratio is 6 divided by 3, which is 2. Check, 12 divided by 6 also gives 2 to make sure it is, in fact, a geometric sequence. So substituting those into the formula, we get Tn equals A, which is 3, times R, which is 2 to the n minus 1. And so there's our formula, which you can't simplify, by the way. You can't write that as 6 to the n minus 1. Be very careful. It is left as it is there, 3 times 2 to the power of n minus 1. And we are asked to find term 15. So substituting 15 in, we get 3 times 2 to the 15 minus 1. So that'll be 2 to the power of 14. And if you calculate that, I believe you get 49,152. Second example, find the 10th term, T10, for the sequence -2, 6, -18, ... You can see this is an alternating series. It's negative, then positive, then negative. Our first term is -2. Our common ratio, 6 divided by -2, is -3. So it's alternating. That negative common ratio will make it go negative, positive, etc. Our formula for our nth term is equal to AR to the n minus 1. And so that's going to be minus 2 times R, which is -3, to the power of n minus 1. So there's our nth term. So if we want term 10, substituting in 10 for n, we get -2 times -3 to the power of 9. And when you calculate that, I believe you get 39,366. That is term 10. Next example. Which term of this sequence, 8, 24, 72, etc., is equal to 52,488? Okay, so identify your first term. Your first term is 8. Your common ratio is going to be 24 divided by 8. So 24 divided by 8 is 3. In other words, you're multiplying by 3 each time to get to the next term. So our nth term is equal to AR to the n minus 1. That's our formula. And we have our nth term is 52,488, and that's going to equal AR to the n minus 1, which is 8 lots of 3 to the power of n minus 1. So if we divide both sides by 8, we get 3 to the n minus 1 is equal to 6,561. The unknown is in the power, so again we're going to go to logs here. We're going to take the log of both sides, so that becomes log of 3 to the n minus 1 is equal to the log of 6,561. We can bring the power down the front using a log law. Now keep it in brackets, it's all that power, n minus 1. So n minus 1 log 3 is equal to the log of 6,561. And now simply dividing both sides, we're going to have n minus 1 is equal to the log of 6,561 over log 3. And so n, you could calculate at that point, but I might just take one line here and write that as n is equal to log of 6,561 on log 3 plus 1, and do all that in the calculator. And you should get that n is 9, and so therefore it's the 9th term. Okay, example number 4. If a geometric sequence has term 5 of 9 and term 9 of 81, find term 15. Very similar to one we did with an arithmetic sequence. Okay, so to start this, we're going to go to our formula. So we have that term 5, which is AR to the 4, AR to the n minus 1, so AR to the 4. We're told that's equal to 9, and term 9 is equal to AR to the n minus 1, so it's AR to the 8, and that one we're told is 81. We'll call that equation 1. And that one equation 2, and we're solving simultaneously. Now, rather than adding and subtracting here, we're going to divide. So if we do equation 2 divided by equation 1, we're going to have r to the power of 4 equals 81 divided by 9, which is 9. So r squared, I'll just take r squared would equal, when I square root both sides here, plus or minus 3. But because it is r squared, it would have to equal 3, because r squared must be, it's a square number, must be greater than 0. So I've taken the square root of both sides. You will notice here, I'm just going to write note, that if I now find r itself could be plus or minus the square root of 3. Okay, there are two possibilities for r here. Two possibilities. You wouldn't need to write this down in an exam, but I'm just making it a note for you here that the r value could be plus or minus root 3. Both will give the same sequence, where term 5 is 9 and term 9 is 81. All right, now we need to find term 15. So let's find a now. We've got the r squared value. So if we I'm going to sub the r squared value rather than the plus or minus root 3. Let's substitute r squared into equation number 1, because it's the simplest substitution. And so we get a times r squared squared, that's ar to the 4, is equal to 9. And so that means that a times, and r squared we found is 3, so 3 squared is 9. And so dividing both sides by 9, we get a equals 1. So our first term in this sequence is 1. All right, and so Tn is equal to a, which is 1, lots of, now it's either root 3, positive root 3 to the n minus 1, or it is possible that Tn is equal to 1 times negative root 3 to the n minus 1, because the r value could be either positive or negative root 3. Now, when we find term 15, that is going to be a outside of r, which is either the negative or the positive root 3 to the power of n minus 1. So 15 minus 1 is 14. You'll notice the power's even. So it's actually not going to matter whether or not it is the negative root 3 or the positive root 3. Both of them are going to give you the same answer here. And so we get, when you calculate that, 2187. So that's the 15th term. Both of those give you positive because it, to the power of 14. Negative root 3 to the power of 14 gives you the same answer. But let's have a look at the next one, because that's not going to be the case in this one. We have term 10 is equal to a outside of r, which is either the positive root 3 to the power of n minus 1, which is 9, or T10 is equal to a outside of minus root 3 to the 10 minus 1. Because r can be, remember, either positive or negative root 3. So if the r value was positive, we would get root 3, that one's going to come out to be 81 root 3 if you simplify that. Or this one is going to be minus 81 root 3 when you simplify that. And so what we can say is that term 10 is either equal to plus or minus 81 root 3. It really depends on whether r is positive or negative, and in this case it is unknown, so we need to allow for it being both, one or the other there. Okay, insert 3 terms between 48 and 3 so that they are in geometric progression or geometric sequence, same thing. So let's picture what's happening. We've got 48, we've got to insert 3. 1, 2, 3, and then 3 there. So we've got 3 numbers now inserted between 48 and 3, and then we've got to make it a geometric progression. So our first term we can see here is 48. And we've got 1, 2, 3, 4. The 5th term is 3. Our formula is Tn equals a times r to the n minus 1. ar to the n minus 1. So that's going to be 48 r to the power of, now n is 5, so that's going to be 48 r to the 4 is equal to term 5, which is 3. So r to the 4, divide both sides by 48. R to the 4 is 1/16. Now, once again, that tells us that r squared would be a quarter. So r is equal to plus or minus a half. We don't know whether or not r is positive or negative. Both of them give you a geometric progression. We'll actually see it here because the question says to insert 3 numbers. So let's take the first case where r is positive a half. Your sequence would go 48, so taking positive a half, times it by positive a half. The next one would be 24. Halve it again, 12. Halve it again, 6. Halve it again, 3. So there's your 5 terms. 3 terms have been inserted between 48 and 3 to give a geometric series or geometric progression. Or if r was negative a half, let's start again, 48, multiplied by negative a half. The next term would be minus 24. Times that by negative a half, positive 12. Times that by negative a half, negative 6. Times that by negative a half, positive 3. So that's an alternating sequence. So here we have 2 possible answers. We've inserted 3 numbers to give a geometric progression. In the first case, where r is a half. In the second case, where r is equal to negative a half. Find the geometric mean of 2 numbers. So very similar to arithmetic mean. You might need to look back to that lesson. Essentially what we're doing is we're going to have 2, then whatever the geometric mean is, followed by 25. And we're trying to find the number in the middle that makes that a geometric sequence. And so x on 2, because remember it's a common ratio, so 1 divided by the term before, so term 2 divided by term 1 must equal term 3 divided by term 2, so 25 divided by x. And so we get x squared equals 50, x equals, now it would normally be plus or minus, but the geometric mean is defined to be positive here. It is defined to be positive. So the geometric mean is going to be the positive square root of 50, which I can simplify to be 5 root 2. So I might make a note, and we did this in the last one with arithmetic sequence. This is the equivalent for geometry. Note the geometric mean of A and B is, and in this one, it is the positive square root of AB. And I'm going to show you again how we arrive at that. If we've got A followed by the geometric mean followed by B, a term divided by the term before it must equal another term divided by the term before it. So just term 2 divided by term 1 equals term 3 divided by term 2. Multiply x by both sides and the a by both sides, we get x squared equals ab, and so x equals, and remember I've said that the geometric mean is defined to be the positive, and so it's the positive square root of ab. Okay, example 7. If these three terms form a geometric sequence, find the possible values of x and the first three terms of the sequence. I should say sequence there. So I might just put a line through that and write sequence. We're going to talk about series later. Okay, so if it is in a geometric sequence, then term 2 divided by term 1 must equal term 3 divided by term 2, because it's got to have a common ratio. If it forms a geometric sequence, and we're told that it does, then term 2 divided by term 1 must equal term 3 divided by term 2, because that's the common ratio. Let's cross multiply now. Cross multiplying, we get x plus 1 all squared is equal to 5x minus 7 times x minus 8. And all we're going to do now is solve this equation. So we get x squared plus 2x plus 1 equals 5x squared minus 40x minus 7x plus 56. Bring that over to one side. We get 4x squared minus 49x plus 55. Just simplifying those terms is equal to 0. So we've got a quadratic. Now always look and see whether a quadratic factorizes. To solve it is usually the quickest. Trial and error here. So 4x multiply to give 55, so 5 and 11. So we'll try it this way. And that would require that to be a minus and a minus, both be negative. So 4x squared minus 44 minus 5 gives you the minus 49x plus 55. So that tells me that x is equal to 5 on 4 or 11. So there's actually two possible values of x. So let's take the first one. If x is 5 on 4, if that's what x is, then the series or sequence, using the word sequence is, well, the first term is going to be x minus 8, so that's 5 on 4 minus 8. The next term is x plus 1, so 5 on 4 plus 1. And the next term, and I'm getting this from the question, is the next term is 5x, so 5 lots of that x value, 5 on 4, minus 7. And putting those into a calculator, we get minus 27 on 4, 9 on 4, minus 3 on 4. It's an alternating sequence, as you can see. The common ratio there you could find by doing term 2 divided by term 1. And you see it'll be a negative common ratio. All right, but there was a second possibility. If x was 11, then the sequence is, right, so we're doing x on 11. So the first term is x minus 8. So that's going to be 11 minus 8. Next one is x plus 1, so 11 plus 1. And the next one is 5x minus 7. So 5 lots of the x value, 5 11s, minus 7. I.e., what's that? Well, that's going to be 3, 12, 48. And that's probably a little bit more obviously a geometric sequence. Its common ratio is obviously 4. And it's not alternating, it's a positive common ratio. Okay, number 8. Find the first term of a sequence 1,500, 250, etc., which is less than 0.001. Okay, so our first term is 1,000. Our common ratio, 500 divided by 1,000, is a half. So our nth term using our formula is AR to the n minus 1. So in this case, it's going to be 1,000 times a half to the n minus 1. And we need that to be less than 0.001. So we've got 1,000 times a half to the n minus 1 is less than 0.001. We're making the nth term less than 0.001. Divide by 1,000, we get a half to the n minus 1 is less than 0. Lots of zeros, be careful. Or 5 zeros now. And so we're going to take the log of both sides. All right, so remember we said log's an increasing function, so the sign will stay the same when you take the log of both sides. So we'll get the log of a half to the n minus 1 is less than the log of 0.12345 zeros. All right, now log law. Bring the power down the front. In brackets, we've got the power n minus 1. Log of a half is less than log of 0.12345 zeros followed by 1. Now here's where you've got to be careful. If you recall, a couple of lessons ago, we drew a log graph. The log graph goes like this, and that is 1. When you take the log of a number between 0 and 1, so this is my x-axis, a bit of a squiggly y-axis there. That's my y-axis. When you take the log of a number between 0 and 1, the answer is negative. You can try that on the calculator. Put in values between 0 and 1 and take the log of it. It'll be negative. So I'm about to divide by log of a half. Log of a half is negative. When you divide by a negative, you must change the sign. So n minus 1 is going to be now greater than the log of 0.12345 zeros followed by 1 over log of a half. Log of a half, by the way, if you look at that, is minus log 2. I'll let you work out why that might be the case, but we can leave it as log a half. And so I'm going to add 1 to both sides. 0.12345 zeros followed by 1. Log a half, and now you can go and plus 1. I've added 1 to both sides, and so when you calculate that, I put an equal sign. That shouldn't have been an equal sign. Let me just go back and fix that. That's greater than there, isn't it? N is greater than. All right, so when we calculate this, we've now got n is greater than, and we get on the calculator 20.93 approximately, and so n has to be bigger than that, and it's got to be an integer. And so therefore, there's going to be the 21st term. The question said to find the first term, which is greater. I now know it's the 21st term, and it's, I'll say here, which is 1,000 times a half to the power of n minus 1. So if n is 21, it's going to be to the power of 20. Just be careful of that. AR to the n minus 1. I won't put that in the calculator. It's obviously going to be very small, but that will be the term. Okay, number 9. Find the first term and common ratio of this. Now, there's two ways you can approach this. One is not maybe quite as clever as the other. So I'm going to show you the sort of most common approach first, followed by a bit of a shortcut. So what you can do, and I'll do this off to the side, you could say that term 1 is equal to 4 to the 1, which is 4. Term 2 is equal to 4 squared, which is 16. And then because I've said find the first term in common ratio, it's pretty obviously a geometric sequence, but you could check that by doing term 3, which of course would be 4 cubed, which gives you 64. And then you'll notice that if I do term 2 divided by term 1, I get that common ratio, get that common ratio of 4. Okay, so that's our common ratio. And so my first term is 4 and my common ratio is 4. But there is a quicker way to do this, and that is to recognize that the question is very close to the format of the general formula for a geometric sequence. It is 4 lots of 4 to the n minus 1. I've just used an index law. That's 4 to the power of 1. I'll put the 1 there so we can see it. 4 to the power of 1 times 4 to the power of n minus 1 gives you 4 to the n. Why did I do that? I did that because if you have a close look now, it is of the form a times r to the n minus 1. And so I can see that this first term is my a and this term is my r, because it's a r to the n minus 1. And so I can read off the first term is 4, common ratio is 4. And you can use that technique for harder questions like this one, B. Keep in mind the formula is AR to the n minus 1. So if I split this off as 5 lots of 2 squared times 2 to the n minus 1, because when I add the indices on those 2's, the 2 plus the n minus 1 gets me back to the original question, which has a power of n plus 1. So I've done that in order to get this n minus 1 in the power. That was the reason for doing that. Okay, so now the next step is to simplify the first part. So 5 times 2 squared, 2 squared is 4, so 5 fours are 20. It is 20 times 2 to the n minus 1. It is now of the form a times r to the n minus 1. So I can see that my first term is 20. Common ratio is 2. Okay, our last example. Alfred deposits $1,000 into a new bank account at the start of 2019. At the start of each subsequent year, he increases his deposit by 5%. Okay, so have a think about what's happening here. The first deposit, the first term, if you like, is $1,000. But it's going up by 5% each year. Now, the quickest way to increase by 5% is to multiply by 1.05. So our common ratio is 1.05. It is not a common difference this time, it is a common ratio. It is going up by 5%. So every time you multiply by 1.05, you are increasing by 5%. So the nth deposit is going to be given by AR to the n minus 1, which is 1,000 times 1.05 to the power of n minus 1. So there is your formula for your nth deposit. Find correct to the nearest cent how much you will deposit at the start of 2035. Okay, so 2035 minus, now we're interested in all of the years up to but not including 2019, because we are including 2019 but nothing before, so we're going to subtract 2018. These are the years that we're not interested in. 2019 onwards is what we're interested in. So that comes out to be 17 years. So there are 17 deposits. So term 17 is going to be 1,000 times 1.05 to the power of 17 minus 1, n minus 1. So it'll be the power of 16. So when you type that in the calculator, don't forget your units, I believe we get $2,182.87, correct to the nearest cent. In which year will his deposit first exceed $6,000? Okay, so this AR to the n minus 1, so 1,000 times 1.05 to the n minus 1 needs to be more than 6,000. Okay, so we've got to solve another exponential equation here. So divide by 1,000, we get 1.05 to the power of n minus 1 needs to be bigger than 6. Take the log of both sides. So the log of 1.05 to the n minus 1 needs to be greater than the log of 6. Bring the power down the front, n minus 1. Log of 1.05 is greater than the log of 6. Now 1.05 is bigger than 1. The log of a number bigger than 1 is positive, so our sign will stay the same when we divide. So n minus 1 is greater than log of 6 divided by log of 1.05. Adding 1 to both sides, we get n has to be bigger than log of 6 over log of 1.05 plus the 1. I've added 1 to both sides. And so therefore n comes out to be bigger. If you do that in the calculator, you get 37.72-ish. And so therefore we need to take n to be 38. So the first deposit is in 2019. So we need 2019 plus an additional 37 years. And so we get 2056. That'll be the year in which his deposit first exceeds 6,000. So now you have an exercise that you can go on with to consolidate geometric sequences.